let me tell you the plan for the day. Today, we are going to spend most of our time talking about Newton's third and very most important law. Got two different activities that we're going to do. We're going to move quickly through them. They are important. They are good, but I think that we'll be able to get it done. Henry at 2:55.
Yep.
You need to make some sort of identification that it's 2:55. Got it? All right. And then just a couple of things. We'll talk about what that means when that comes up. Here's the homework. It's also on Canvas for Monday. On Tuesday, that's what we decided is when you're going to take your test. The test is going to be over the impulse momentum. I think I had typed the word theorem. It must have gotten erased somehow. Conservation of momentum and Newton's third law. Those are the big three things. They're really all one and the same. You're going to see that today. But anyway, those are the three big things that could potentially, probably will be on the test on Tuesday. Okay? We're going to get started right now. Question.
So what will Monday be? Like a review day?
We're going to talk about it at 2:55 when you let me know that it's 2:55, right? Yeah. All right. So, Miss Carveling's least favorite Winter Olympic sport. No. No.
Yes. It's a skiing one where you jump off the big ski ring.
No, that was awesome. That's up there, but it's not my least favorite. No.
Cross country skiing.
Nobody ever gets it. Curling is like the best.
Yeah, curling. Figures curling.
You're close. All right, I'm going to take away this pain of listening to you just yell at me. My least favorite Winter Olympic sport. A lot of people don't even know that it's a sport. So, like an Olympic sport. I discovered it, I don't know, a long time ago, and I realized that I didn't really enjoy it. And I'll explain why as we go here. So, I enjoy watching lots of the sports. The thing that I enjoy watching the least, and I want to put a caveat on there because I could never do this sport, and I don't know if maybe one of you is, like an Olympic hopeful in it, and I don't want to offend anybody, but my least favorite Winter Olympic sport is ice dancing. Now, I don't know if you know it, well, and he said figure skating, but figure skating and ice dancing are fundamentally different. And I don't know if you're aware of that. I enjoy watching figure skating. Figure skating, they jump, they spin, they do all kinds of things, and in pairs figure skating, they can throw one another, right? Which is exciting. The trouble with ice dancing is that it's always a pair sport, which is fine. Like that doesn't bother me. My understanding of it, and correct me if I'm wrong, if anybody knows about ice dancing and I'm wrong, my understanding has always been that in ice dancing, each partner has to have at least one skate on the ice at all times. That means no jumping. That means no throwing. That means all of the excitement is gone. And so that's the first problem. The second problem is that 90%, and that may be an exaggeration, but I'm going to say 90% of all ice dancing routines start off in exactly the same way.
Yeah, they do that so it's easier to judge.
Are you an ice dancer?
I dance, but
Woo!
well, I used to.
You used to ice dance?
No.
Or just regular dance?
Just go
Oh, okay. Dancing, that's totally different. Because you can do things. Yeah,
like
yeah.
my mom said, in reality, dancing competitions should be judged how, figure skating and stuff like that should be, because it's all the same. And all dance routines are different.
Right.
I like your
interesting. All right. Okay. So let me get back to my story. Not because I think that's fascinating.
Yeah.
But the other part of ice dancing that I am not a fan of. It's the same reason that I really enjoy watching mafia movies and romantic movies are not my thing. My husband makes fun of me when we watch a movie. If it's an action movie and then there's the requisite love, love interest story, I'm this is dumb. No. A good romantic comedy now and then's fine. But you don't need it. Just do the fun stuff, right? So the problem with ice dancing is that, again, 90% of the routines start off the same way. So you've got the two people, right? Because it's a partner sport, and they're standing there and they're gazing into each other's eyes. Right? And then the music starts. starts. And then there's like 2 seconds of good physics, and that's the part I care about. But the whole like gazing to each other's eyes part, whatever. Okay, the music starts, and what happens?
They push the charge.
They push off, right? So that's like the 2 seconds of okayness, and then whatever, and then I just turn it off. So I'm like, whatever, it doesn't matter anymore. So I want to think about those 2 seconds because that's really all I care about. Okay, so you got the 2 people. They're standing there. They're standing there prior to the music starting. So let's draw them here. We're gonna just let's. We're gonna name one of the 2 dancers, ice dancers. We'll name her Alice. Now, prior to the music starting, she's just standing on the ice. Quickly, so fast, draw a Freebody diagram of Alice. What forces are acting on Alice? You got this. You got this. So you've got the force of the earth. Which way does that one pull or push? Goes down, right? All right. And then, what else do you have acting on Alice right now? No music has started?
Applied force.
No music has started.
I mean, end force. The
what?
natural.
The what? Kate, what did you say? The surface.
Normal force. See,
There you go. The reason I gave you that look is because I never understand when a student says natural because we've never said that word ever. But you, like, they always do that. I don't know why. Normal force, the ice on Alice is going up, the earth on Alice is pushing down. How do those 2 forces compare? Equal in magnitude. You know that because she is not what? Accelerating. You guys are good. I love this. All right. So then we'll do the other person and
name him Chad.
no.
Billy.
Oops, that's too far away.
Craig. Name him Craig.
Who said that? Craig.
Name him Adam. Yeah, Gabe. Name him Gabe. Richard.
When I was a kid, the ice dancing and all of the figure skating events were always the Russians were always the best. They always were. I'm not saying they are now because I honestly don't watch ice dancing anymore because I'm just tired of it. It's like, but no, because this one's B and that one's A. See, yeah, it's like I've done this before or something. All right. So what forces are acting on Boris? Same, right? The force of the earth on Boris. That's an FG. The force of the ice on Boris. FN. All right. And how does Boris's FG and Boris's FN compare to one another?
Equal.
They're equal, right? Because we know that he is not what? Accelerating. Now, quick question for you. How does the earth on Alice compare to the earth on Boris? It does depend on their mass. Now, we can make some assumptions, and we need to make some assumptions so that we can move forward. So we can assume one thing or another. I don't really care. Let's say that they are not the same mass, just because that makes it more interesting, right? What's that?
No, Boris is smaller.
We're going to say Boris has a less mass?
Yeah.
All right. All right. How are we going to care? I don't care. You want to say Boris is smaller?
Yes.
Okay, the mass of Boris is less than the mass of Alice. So I'm going to just put this here. I'm going to say boop, boop. Okay, awesome. Fantastic. Now, this is before the music has started. They're just standing there gazing into each other's eyes, whatever. All right, and then the music starts, and then you told me that they push off, right?
Yeah.
So that means that now we've got more forces acting. True? True. We've got more forces acting. So what do we have? So on Alice, what's acting on Alice now?
Applied force.
But remember, hold on, we got to back up. A force is an interaction between how many objects? Always 2, right?
Yes.
So what object is acting on Alice? Boris, right? So there's a force Boris? It's going which way?
That way.
Left.
That way, right? And at the same time, maybe, I don't know, there's another force on Boris. Who's it from? Oh. Okay, life is good? Okay. Who said no? Okay. Are you actually okay, or are you confused already? That's why it's on the ice, right? They just Zambonied the ice. Okay? They just sharpened their skates. So we are going to say that friction is nearly
Negligible.
0. We're going to get rid of it. We don't want it. No time for it. All right. A few questions for you, my friends. Question number 1. Question number 2. Talk at your table right now about those 2 questions. Go.
Are these the last two
I don't ask trick questions. I ask questions.
One of the focus. Can't stop for just.
Yeah.
Are these the last dimensional answers?
I'm wrong. I'm gonna write it
Wait.
I wish I could be so sweet.
That's
Then it would just be
Right now, they're like,
Harder to this year. No,
it's like
my favorite.
They're like, wait, they're really,
I'm going to give you 10 more seconds.
You'll just sit on you. That's all.
And Boris is going.
All right. Scientists, I'm going to grab your attention because we got to get started again. All right. So the first question 1, who pushes first? This one is directly, this may be useful and applicable to you on a daily basis. You may have outgrown the need for this question, but I do want to point it out to you. So what did you talk about? Who pushes first?
Me.
Who pushes first? What did you say, Jasmine?
I said neither.
Why?
Okay. Well, so like if,
No, guys, listen, please.
well, if Boris, so if they're both kind of about to push each
Standing there gazing into each other's eyes, yes.
other, so when they apply the force, Boris he pushes Alice, so she goes backwards. But at the same time, Alice is pushing back on him, so he goes backwards. So it's not like one pushes and stops, and then the other pushes back.
Right. Who pushes first?
at the same time.
Same time.
Dude, that's
The particularly applicable piece to this, if you happen, so I have, full disclosure, I'm an only child, I don't have any siblings, so this has never actually happened to me. But if you have siblings, it is my understanding that often there is strife between siblings, and my understanding is that sometimes it becomes like a physical interaction, right? And so my understanding is that sometimes, this is based on, just watching TV shows and things like that, my understanding is that sometimes there are these little petty fights that happen where it's like, Mom! What? He pushed me! Well, he pushed me first.
That's never fight.
And so what's really the truth? You walk up to your little brother, your little sister, maybe your big brother, your big sister. No, I bet it's not you. You guys aren't picking fights. Your brother or sister walks up to you and bumps you, right? Oh, but they don't know physics, so it's totally you. Yeah. You bump them, and then they go and tattle, right? Well, he pushed me first. Is that really true? No! Nobody pushed first. At the moment that I might have bumped into him, What did he do to me? He bumped into me at the exact same moment.
Wait.
Just saying. I'm not saying that maybe you didn't instigate, but the actual pushing, right? He pushed me first. It's not a thing.
But did he?
It's not a thing.
I'm spinning around with my fists out, and if you walk into my
I can totally see that. That's really funny. Oops! I don't know. You were right there. I don't know what happened.
Wait, I have a
Right, but okay.
It doesn't make any sense.
Ladies and gentlemen, my friends, I need you to be quiet so that I can answer this question. Question, go.
Wait, can I demonstrate?
Yeah. No, you may not demonstrate, but you may talk.
Okay, it's hard to explain. So if I'm walking,
Yeah.
I'm going next to somebody,
Yeah.
and I don't like them, then I go like that and put my shoulder through them.
Yeah.
Are we both pushing off of each other?
Yes.
Yeah. That's what I'm saying.
Because his shoulder's going back and my shoulder.
You're still, yeah.
If that happens, you feel it, right? The reason you feel it is because there was a force applied to you as well. I'm not saying.
But my shoulder's okay. So his shoulder's going back, my shoulder still gets going in the same direction.
Somebody can be pushed harder.
Yeah, because you're putting.
Well, that's question 2. So let's do question 1 first. One at a time. So who pushes first? The answer is neither one, right? Neither or both. I guess you can say it either way, okay? Forces. Forces appear, or come, I'm going to say, in pairs. And they, what do I want to say? They start at the same moment. Okay? Here, let's say this in a different way. Forces, I know it's mean, right? I erase things, I'm sorry. I need a better verb. Appear are...
Fizzle out of it.
Appear, I guess, is the best. Form, no. Appear. Only. Okay. Occur. That's the verb I wanted. Thank you.
Good job, man. No, it was you, man. It's all you. It was all you.
Okay. I need to grab your attention. I need you back here because we've got a lot to do today. Okay? So the forces are going to occur in pairs. They start at exactly the same moment. Let me ask a follow-up question to this. Who pushes for a longer amount of time? How long does the force last? As soon as they are not touching anymore, there is no force, right? Yeah. So not only do they start at the same time, but they end at the same time. So they last exactly the same amount of time. Okay, at the same moment, and they last for the same.
Would it be different if one was accelerated?
We're going to figure that out. We're just talking kind of in this case, right? Okay. Question 2 is the bigger puzzle of a question. So here is the situation again. Alice is standing, Boris is standing. It says that you have to be careful here, friends, because I don't want you to make incorrect assumptions that are going to lead you to the wrong answer. We decided that the mass of Alice is greater than the mass of Boris, right?
Yeah.
Just want to make sure that that's in your head, because I will tell you that usually when I do this lesson, we make the assumption that Boris is larger. Often I just kind of lead people down that path, and then they're like, oh, and then we make these, we just start making assumptions about people, which is not always true. We are making this assumption, right, that the mass of Alice is bigger than Boris. Now, given all of that, who pushes harder?
Boris.
I'm going to vote, because I feel like I'm going to hear other stuff. Raise your hand if you think it's Alice.
You're wrong.
Boris the animal.
Raise your hand if you think it's Boris.
Yeah, be right.
What did you say? Raise your hand if you did not raise your hand before.
You all should be shy.
Oh,
They don't.
okay. All right. So, guys, you need to be quiet.
It requires more physical action.
So I saw some votes for Boris, and I saw some votes for I didn't vote. So can somebody can you defend your answer? Go, Nick, what you got?
Well,
What did you vote for, first of all, I guess?
Boris.
Okay.
Boris is pushing a heavier mass than Alice is, and so it takes more force to push a heavier mass. And so I think Boris exerts more force into the push.
Okay. Do you guys agree?
Yes.
I hear some yes, I hear some no. If you said no, then raise your hand and defend something else if you disagree.
I don't know. But like when they push the same amount, just Alice wouldn't go as far because she's like she weighs more.
So, okay, so you said wouldn't they push the same amount? And what was your reasoning?
Because like I don't know, just as a result.
Hold on, I'm sorry. My friends, we're learning as a group, which means that you need to be quiet. If you want to share something out to like add to this conversation, I'd love for you to do it, but I want you to give full attention to Ellie's response because I want you to know and I also want to be able to hear it. Go ahead, right here.
So like wouldn't Alice just not go as far because she has lower mass. And
Thoughts? Yeah.
I think like the total force would just be like one thing would be the same, but like with the way this is worded, it's like who's putting in more effort in the push, I guess. But the push itself will stay the same. If that makes any sense.
Tell me more because it doesn't quite, but I'm not saying that it's wrong. I'm just trying to tell me more.
I don't know what to say.
Sorry.
If so, like, if Boris were to put in more effort, the effects would still be the same on Alice. Like, it would still be one push.
So you're arguing for this one or this one? I'm confused about which one.
Same.
This one.
Yeah.
Can you look confuzzled? Can you tell me what's going through your head?
I just couldn't read the board.
Oh, okay, fair enough. To figure out what in the world this was. Okay, yeah, that's fair. That's fair. Do you need me to help you, or are you okay?
No, I'm good.
Okay. Gotta go.
Well, I think it's the same amount, but I think Alice, it's not that she necessarily needs to go as far, she just has a lower velocity.
Conservational momentum.
I don't know which one you're right.
Wait, what did you just say?
Conservation of momentum.
Oh.
Why don't we think of this before?
Oh. Let's find out, shall we? Oh, I love it. We can put things together. So, my friend Cole over here is like, oh, well, we talked about this kind of. I hope at this point in our time together in this unit, you are convinced that the conservation momentum is true and it's real and it works. And it's, I mean, you saw it with a bunch of different videos and there were a bunch, 20 videos that we compared all together. So I kind of think that that's probably okay. So what does conservation momentum say? Let's see if we can get to that from conservation momentum. She says with excitement, initial momentum equals final momentum. All right. And then what?
And every step along the way.
Okay, so let's go from there. What does that mean? What is momentum? Mass times velocity, and it's how many different objects are we talking about in this story? 2. So we got the mass of Alice times the velocity of Alice at the beginning. I'm going to write it out. You can write it out with me. This is the mass of Boris times the velocity of Boris at the beginning. is equal to the mass of Alice times the velocity of Alice at the end plus the mass of Boris times the velocity of Boris at the end. That's why I wanted to use Alice and Boris and not Alice and whatever you were saying before, because it's easy for me that way. All right. Now we could set these equal to 0, couldn't we? Because Alice and Boris are standing there. But Henry pointed out something interesting before, and that was, what if they were moving to start? So I'm going to do the most general case that I can so that we're not making any other assumptions. I think that this is true, so let's just keep going with this. It's going to require more subscript writing, but we can handle it, okay? I believe it. Because I've done this a couple times and because I believe in what I'm doing, I'm going to go ahead and move all of the A stuff to one side and all of the B stuff to the other side. Is that okay with you? Okay, so let's do that. So I'm going to say the mass of A times the initial velocity of A minus the mass of A times the final velocity of A. I switched the way that I did my subscripts. I hope that didn't screw you up. I apologize if it did. The mass of B times the final velocity of B minus the mass of B times the initial velocity of B. Is that okay? Did I screw anything up? Because I have screwed this up before, so I want to make sure I'm okay. I'm going to pull the masses out from both sides. So the mass of A times, I'm gonna be a little wild and crazy here. So stop me if I'm going too nuts. I'm gonna change that to a negative, and I'm gonna flip them. So I'm gonna pull a negative. I'm gonna factor out a negative sign because I know that it will help later. Negative. So that's gonna be VF. Oops, let me do that in purple. Equals the mass of B times VF for B. Bless you. VI for B. Bless you again.
You're welcome.
How are we doing? I didn't do anything like this. We're just doing algebra, right? This change in velocity occurs over a time, doesn't it? How much time did it take for Alice to accelerate? How does it compare for the time it took for Boris to accelerate? How did the times compare, Nick, would you say?
They're the same.
The same? So I'm going to divide by T on both sides because I can. And because it'll be nice to do that. Because what is VF minus VI over T?
Velocity. Acceleration.
Acceleration. So now I can write this up like this. So I can say that the opposite of the mass of A times the acceleration of A equals the mass of B times the acceleration of B. Oh, that's nice and pretty. Science is happening right before your eyes here. Hey, what's mass times acceleration, you guys? I heard somebody say, but I don't know who was.
Force.
It's force? It is. So this is saying that the opposite of the force acting on A, the net force acting on A, what force is the net force acting on Alice? The net force acting on Alice. Who's acting on Alice that's causing a net force? Boris, right? The force of Boris on Alice, because these guys cancel out. You with me there? So it's just the Boris force. Right? I know. It seems like a thing. Should be a thing. Is equal to the force of who is acting on Boris? Net force is just Alice, right? How are we doing? That was what? Something?
That was tedious.
So many things to nothing. So now let's take this and figure out what we're going to do with it. What does this really mean? The force of B on A is equal to the opposite of the force of A on B. Who pushes harder, ladies and gentlemen? Nobody pushes harder. The answer is that they do push the same amount. Now, I just showed it to you mathematically. You may or may not be convinced with the mathematics, but your inclination, your gut feeling, very rarely relies on mathematics. So I want to ask another question. We'll come back to Alice and Boris in a minute. How many of you have driven in a car? Or ridden in a car? Maybe you don't drive, but you've ridden in a car. How many of you have ridden in a car during the summer? How many of you have ridden in a car in the summer and the evening, at night? And how many of you, while you've been riding in a car at night in the summer, have happened to hit a bug?
Oh, you got me.
Did I get you? All right. I want you to imagine that experience. So here comes the car. This is the windshield of the car. Here comes the car. Here's a bug who's just flying along, minding its own business. It's a beautiful night. Da-da-da. Are you with me? Does the bug feel an applied force?
No, it feels death.
Let's think about it. Let's think about it. Point taken. Not from a philosophical perspective. Let me change the verb. Does the bug experience an applied force? Yes. Okay. How do we know? F net over m equals A. Does the bug accelerate?
Yeah.
Indeed. The bug was flying this way. Happy, happy, happy. Now he's that way. Are you with me? He was. Boom. Okay, so the bug has felt a force. Okay? So the car applied a force to the bug. Does the bug apply a force to the car?
Yes.
Which force is bigger? Which force is bigger?
Neither.
But did you catch this? Some of you were like, wait for it, I gotta think about the math. Some of you went with your gut feeling, and your gut feeling told you that who applied a bigger force?
The car.
Right. Why?
Because it's bigger.
Because it's bigger, and so which one, so what is, whoa, that was exciting. What is bigger in the story? What do you see that happens to the bug? What happens to the bug?
Dies.
It dies. From a physics perspective, I don't care about the life or death of the bug. All I care about is the motion of the bug. From a physics perspective,
It accelerates.
it accelerates. And its acceleration is ridiculously big. Are you with me there? Okay, so the thing that I want you to write down, the important piece of this, friends, is that we see acceleration. We see acceleration. That's the thing that our brain can internalize because we see the bug going this way and then we see the bug going that way. We don't see force. We see acceleration. And we see that the acceleration, which is equal to F net over m, we see that the acceleration is big, so we assume that the force acting on it had to be really big. But in fact, if we think about the acceleration for the bug versus the acceleration for the car, the acceleration for the bug is really, really big because the mass of the bug is really, really tiny. Are you with me there? Okay. The acceleration for the car, so let's think about this. Think back to the summer nights when you're driving and you're smashing all these bugs. Every time that a bug meets its end on your car windshield, do you feel that? Like while you're driving? That does not happen. Are you with me? Like that's not a thing. It would be much less pleasant to drive if that were the case. Like it doesn't, you know, why not? What would that do be? That would be your acceleration, right? Does your car accelerate every time you hit the bug? Be careful. Yes.
Yes.
But tell me about the acceleration. So little, right? It's so little. Okay? So the forces are the same, but we see the acceleration. So you have to separate those two in your head. Acceleration versus force. Okay? How are we doing? We okay? Okay. Now, I've got just a few minutes before Henry's going to be really loud, so I need to say a couple things here. First of all, this all led us to, or the whole point of this was that we were going to discuss Newton's third law. Okay? You may have figured out in the few months that we've known each other that I don't like to recite laws, right? I don't like to recite Newton's laws because I don't think that you learn them right. Every time that I have this conversation with students, I hesitate to even bring it up. But I'm going to bring it up because I want to point out to you the flaws in it. Okay? And I'm not trying to demonize your science teachers of the past part of your life. Like, I'm not trying to say they're wrong, but I want you to realize what you're saying and why it's misleading. So if I had asked you at the beginning of the period to tell me what Newton's third law was, some of you would be like, I don't know. I don't know. Some of you would recite something. Does anybody know what the nasty thing? I only want to hear it one time. Does anybody know what the thing that you want to say? Who's going to say it? Oh, man. Oh, Rudy, are you going to do it? Go.
Every force has an equal and opposing force.
Okay. That's okay. That's the okay-ish way to say it.
Every action has an equal and opposite reaction.
That's the yucky version. So what Rudy said is okay-ish. But that other ickiness that happened over here, I just want to point out to you why I don't like it. First of all, what in the world's an action? Like, that means nothing, right? You know what a force is. A force is an interaction between two objects, okay? A force is an interaction between two objects. The worst part of the recited Newton's third law is the last word. Every has an equal and opposite, and then there's the word. What is that word?
Reaction.
Yeah. The thing that I really, really don't like about it is the prefix on that word. The prefix re. What does re mean? Rebound, retake, redo. It means again, and generally it's implied that it's also after. You with me there? Yeah? If I bump into Idris, I apply a force to him. Does he apply a force to me? Maybe. Not even maybe. The answer is really what?
Yeah.
Yes, of course. The forces are exactly the same in size, aren't they? Indeed they are. Exactly the same in size. Opposite direction, right? And which one happens first? Same time. Got it? That's what you need. This is what you need to know. This is Newton's third law right here. Okay? So label that Newton's third law. What did you say? Oh, that's great. Okay. One more piece. One more piece. Sometimes when we're talking about Newton's third law, we talk about these things as third law pairs. Okay? F of B on A and F of A on B are what we call a third law pair. Okay? Those are Newton's third law pairs. Two objects, and the forces are acting on opposite things. Alice on Boris, Boris on Alice. Car on bug, bug on car. Okay? Got it? Okay. I've got time for one more thing, I think, before crazy noises are going to happen. So, I would like, what do I want to do? I'm just going to get the frog out. All right. I'm going to set the frog right here. Just a nice little review for you. Draw a Freebody diagram of the frog, will ya? Like, I could flip a few pages behind. I've done this about 12 times.
I approximate this frog to the shape of a cube.
Perfect. All right, quick. Freebody diagram of the frog, make it happen.
Like one day you're just gonna burn the frog and you're gonna go
I have had that frog since I was your age. Do you know that?
Whoa.
Yeah, I was a sophomore. Actually, I was younger than you. I was a sophomore in high school. He's been around a long time.
There's some sophomores in this class.
Yeah. So, the same age as some of you. All right. Did you get a Freebody diagram of the frog drawn?
Yep.
Great. Compare your Freebody diagram with your partners. Go.
That's all you got?
Disconnected? No, first, guys, we
All right. My last question for you and your part. Well, I have two. First question is, how do the forces that you've drawn compare? And my second question for you is that a Newton's third law pair? Go ahead and have a conversation. Go.
You see in 2D, but you feel like 3D. If you were in a 2D world, where you're able to 3D, if you're in a second dimension, the table body of the rocket
All right. Ready? So you have two forces. The two forces you drew on your frog were what and what?
Gravitation.
The gravitational force, the force of the earth on the frog. The other one was the normal force, the force of the table on the frog. How do those two forces compare? They're equal in magnitude, opposite in direction?
Yeah.
Okay. All right, we're 2 for 2. Third one, are they a third law pair?
No acceleration.
Oh, I'm getting mixed messages here. Raise your hand if you say yes, it's a third law pair. Raise your hand if you say no, it's not a third law pair. Defend your answer. Somebody?
Trial by combat?
No. Trial by grains, I want to know why. Is it a third law pair? Who's got it? Come on. Liam, you start, and then we'll come back over here. Go ahead.
No, it's not, because when we're talking about the frog, we're talking about the relationship of the frog and the earth, and then the frog and the table, instead of just two objects.
Oh. So you said the force of the earth. I'm trying to get out what you said. On frog.
Yes.
And the force of the table.
It's not the two forces. There's force.
Okay, so I just want to make sure I understand what you said. So say it one more time now that I've got this picture here.
So it's not very well here because we're talking about the earth on the frog and the table on the frog instead of just between two objects.
Does that make sense? Mm-hmm. So this is a free body diagram. If I have the frog here and I have the force of the earth on the frog, what would be the third law pair force? Say it loud. The force of the frog on the earth. You with me there? A on B, B on A. So the earth on the frog pulls down. Which way does the frog pull on the earth? Up. The frog pulls up on the earth. There's the earth.
Well, we consider the table part of the earth.
Consider the following.
Well, maybe the table is exerting its gravitational force on the rock.
Okay, hold on. You're trying to disprove something, but you're not in the right spot. So hold on just a second to that, okay?
Okay.
Okay? So, because I want to make sure, I don't want to miss. Thank you. You're wrong. You're like 35 seconds early. Come on, Henry. All right. All right, this whole parallax issue again. All right. You're not going to do it again. Ladies and gentlemen, I need your attention right up here. I don't want you to miss this point. This is a really important point. Thank you for the loud noise to notify us at the time. But I want to make sure that you get this because this is not trivial. Okay? The force of the frog on the earth and the force of the earth on the frog is a third law pair. A on B, B on A. That's a third law pair. Okay? If you have a free body diagram, all of the forces are acting on one object. So whenever you draw a free body diagram, everything is going to say the force of blank on that same object. Okay? Force of the earth on the frog, force of the table on the frog, force of your hand on the frog, force of da-da-da on the frog. Everything's about the frog when you're drawing a free body diagram. When you're doing a Newton's third law pair, it's just two objects, force of earth on frog, force of frog on earth. The Newton's third law pair, if I'm pushing on a chair, force of carbling on chair, what's the third law pair that goes with that? Chair on carbling. Even if I'm pushing the chair this way, it does not matter. The chair is pushing back on me. How do those forces compare? They are equal. The forces are equal. Our accelerations might not be, but the forces are equal. Okay? I want to make sure that's in your head because a lot of times that gets mixed up. Last question before I move on to the other thing. Last question. Will there ever be a Newton's third law pair in a free body diagram?
No.
No.
Will you ever have a Newton's third, like both forces of a pair on a free body diagram?
No.
Gunnar, go ahead.
Can you have a free body diagram of one object?
Nope.
No.
A free body diagram is one object and all of the forces acting on that object.
No.
Or a system, I should say, right? It could be a system. Like when we had those two boxes with the string in between them and we talked about it as a system, right? Then that inside force doesn't matter. So no, you cannot have a Newton's third law pair of forces on a free body diagram. Might be worth writing down. I'll write it down too. Okay? You cannot have a Newton's third law pair of forces on a free body diagram.
To be like the same quote unquote type of force.
What do you mean?
Well, we have a frog sitting on a table here, and like
Yep.
a vacuum, there's no other gravity.
Okay.
Assuming that the table is like the new Earth or something.
Okay. Keep talking.
The frog is still sitting on the table because it's gravitational attraction to the table, and the other way around also. So would the pair also, would the third law pair be like manifested as part of the normal force as well?
I would say no, because they're two different forces. There's a force, there's a gravitational force between the center of masses, and the normal force is technically an electrostatic force between the electrons in the bottom of the frog and the electrons at the top of the table. So they're two separate forces. Yes. Yes. Yeah. So you're saying the Newton's third law pair needs to be the same type of force? Is that what you said? Yes. Then I would agree with what you're saying. Yes. Elizabeth, question?
So in the one I said about over there is gravity and stuff. So the Earth and the frog are a pair, and the table is exerting a force on the frog.
For sure. And the third law pair force with that one would be frog on table. The frog is pushing down on the table.
But the force of the frog on the table is just the force of the Earth and the frog.
They have the same magnitude and they have the same direction, but they are not the same force.
It's the earth.
It's not. It's weird. They have the same magnitude and they have the same direction, but they are not the same force.
Like, so is it double that magnitude?
No, so, okay. Okay, hold on a second. It's a good question. So here's the table. If I'm talking about what's happening to the frog, the only things that I'm going to talk about are the earth and the normal force, right? If I'm talking about the frog, this is all I care about. If I'm talking about the table, there was a problem that we did on a test a long time ago where it was like, what's the normal force of one block on another or something like that? So if I'm talking about the table, what forces are acting on the table?
The force of the earth.
There's a force of the earth on the table.
And the force of the table on the earth.
What else is acting on the table?
Normal force.
Yeah. Does that make sense? The frog, if the frog is still sitting there, the frog is also pushing down on the table.
Because the earth's only.
Yes, but it's not the same force. That's the thing that I want you to get. It's not the same force. It's the same size and the same direction, but it's not the actual same force. It's not the same cause. Yeah.
So like just to be clear, if you drew the earth under the table,
Yep.
so the earth pushing up on the table and then the table kind of pushing down on the earth, that would be a Newton's third law there.
Say that one more time.
Okay, so like if you drew the earth, so the earth pushing up on the table and then with the same magnitude, the table pushing down on the earth,
That's a third law pair. B on A on B. Yep, they always have to be the same two objects.
So
Okay.
what were you saying about the frog? I didn't really.
Holy cow. Oh my gosh. Okay, whatever. Go ahead. Keep talking.
This. What were you saying about the second picture? I don't. With the frog, I didn't catch it.
That the frog is also pushing down on the table, which is actually causing the normal force of the table on the legs to be bigger. Yeah. All right, ladies and gentlemen, I want you to listen very carefully because I got just like 35 seconds left. To be clear, Monday you need to do this homework for Monday. I'm going to adjust this, but we're going to do something with the video analysis that's going to require you to understand Newton's third law on Monday. Tuesday we're going to test. Then we're going to start on energy on Wednesday. Okay? This is not going to be super high stress. I don't know if that'll be high stress as a test. You know, that was like the perfect. Like, can I just take a picture of that and put that on there because it was perfect?